So here's what happens in 3.6 is we've learned all these derivative rules, but then in 3.6 there's 6 more rules because, well, first of all, there were 6 trig functions. Seems like it's funny, every time I say the word 6 I go like this. Like you guys don't know what a 6 is. Anyway, there's 6 trig functions, of course, and we learned how to do their derivatives. What happens in 3.6 is they tell me about the derivative rules for the 6 trig inverse functions. So it's like 6 more memorized rules in a way. We can talk about this over the next week. I like you to memorize a bunch of rules. I'm thinking, though, that maybe I don't make you memorize these 6. Maybe I figure out a way to let you have these. But maybe that'll relieve a little bit of what you have to memorize, because I guess I'm asking you to memorize everything else. But what are these things? Here's what we're talking about. We're talking about this function, y equals the arcsine of x. Now, that's one way to write it. The other way to write it, and we reviewed this back in our review, back week 1. We reviewed a little bit of these ideas. The other way to write it is sine inverse of x. So this is a trig inverse function. Well, I'll just tell you the truth. His derivative is this. Y prime is 1 over the square root of 1 minus x squared. That's the derivative of this function. And it's kind of weird and out of the blue, seems strange. It's just some memorized formula. And you can treat it like a memorized formula. Perhaps you'd like to understand a little. So I think I'm gonna show you something. I'm gonna sort of show you the proof of why this is the derivative. Okay? I don't think I'm gonna run through this proof for all 6 of them though. Well, there's 6 again. I think let's prove one of them. Maybe I'll prove another one later. But let's do it. So here's the proof. So hang on. So y equals the arcsine of x. You know, oh boy. You know what that means? It means this. So this is equivalent to x equals the sine of y. I don't know how you like to think about that. You could, so first of all, though, you got to believe that. But how do you want to think about it? Maybe you think about it like this. Maybe you say you took the sine of both sides. Maybe that's what you did. And on this side, you get the sine of y. And over here, you have the sine of the arcsine, or the sine of the sine inverse. And the sine inverse are inverses, so they cancel each other out, leaving me just x. Of course, I wrote it backwards, didn't I? The sine of y equals the sine of this, which is just x. Or you can think about it like this. You should understand these inverse trig functions. On trig functions, listen, on trig functions, on trig functions, you plug in angles and they spit out numbers. You plug in 30 degrees, it spits out a half. That's what trig functions are. You plug in angles and it spits out numbers. And what those numbers mean, the ratio of the hypotenuse over the, there's a whole story about what those, but you plug in angles, it spits out numbers. So the inverse function is you plug in numbers and it spits out angles. So this angle, y is the angle whose sine is this number. And then this says the sine of that angle is this number. Anyway, this is the same thing. All right, so what did I do? I'm trying to prove his derivative. But what I did was I rewrote it. I rewrote it like this because it means this. And now I'm going to do this derivative. Okay, how do you do it? And I'm going to do it implicitly, maybe, as you can tell. I'm doing it implicitly. Hey, what's the derivative of an x? With respect to x, the derivative of an x is 1. Thank you. What's the derivative of a sine of y? It's a cosine of y, dy dx. That's how you do an implicit derivative. Okay, good. All right, so where's the slope? Where's the derivative? It's this dy dx right here. So this dy dx is 1 over cosine y. So that's the derivative of that function. That's the derivative of that function. Now wait a minute. That doesn't really look like what I said. I said that, right? All right, hold on. I'll prove that to you. What am I going to do to prove it to you? What I'm going to do to prove it to you is I'm going to draw a triangle. This sentence or this sentence both say this, that there is an angle y, and the sine of that angle y is x, which is opposite over hypotenuse. So that's because it's sine, and it's x. So I'm going to put opposite over hypotenuse, because it's x, it's an x, which is like an x over 1. I'm going to do Pythagorean theorem to find the other leg of this triangle. You know, Pythagorean theorem would be the hypotenuse squared minus that leg squared, square rooted. So the other leg of this triangle is 1 minus x squared, just using Pythagorean theorem. Now, stare at this picture that you drew. You drew this picture from these relationships. They're the same relationship. Anyway, we drew this picture. Now let's go over here and fill this in. What's the cosine of that angle y? What is the cosine of that angle y?
It's the
adjacent over hypotenuse? Oh, I'll be damned. So the cosine of y is this square root over 1. So the cosine of y is this square root. And that's, so now you're done. I just proved it to you. I mean, the derivative of this guy is this. Truth is, I would memorize it. But, well, except I just told you a few minutes ago, maybe I'd let you have it. But I'd memorize it. But I might give it to you. But here's the proof of it. This is the proof of it. And it's not a bad little proof. You start with this idea of rewriting this, and then you take an implicit derivative, and then but then there's this trick of drawing the triangle. Could you draw a triangle if you had y equals the arctangent of x? Could you draw a triangle? I don't even want to go through the whole proof, but can we draw a triangle for the angle y? This is the angle y whose tangent is x. So because now it's tangent and the answer is x, I would put opposite over adjacent, x over 1, opposite over adjacent, and then put that, now these are the two legs of the triangle, so the hypotenuse is the square root of him squared plus him squared instead of minus, right you guys?
Right.
Because I'm building the hypotenuse out of the two legs here. And yeah, that's the triangle for this picture. I mean, that's the triangle for this function. That's the picture of this function in a way. What did I say? I didn't want to prove it to you? So I'm skipping all these steps. Anyway, the final answer is the derivative y prime is, this time, it's 1 over 1 plus x squared. That's the rule for arctangent. So I skipped over all the little proof steps. I just, and now you're staring at me weird. Maybe you like that little proof. It made sense to you, didn't it? And this time I skipped it. Here, I'm sorry. Let me not skip it. You ready? How do I prove this? Switch x and y. Well, not really switch x and y. Rewrite this. When you rewrite this, you could say that x is the tangent of y. Is that what I'm saying?
Right.
Y is the arctangent of x. So x is the tangent of y, the angle y. And there's a picture of the angle y. And now I want to do an implicit derivative. You ready? The derivative of x.
1.
The derivative of the other side. You guys know the derivative of tangent.
Secant squared.
Secant squared. You should know the derivative of tangent. It's secant squared. Secant squared of y, dy dx. If I want dy dx, which I'm trying to prove, then I think I should divide by that secant squared. I get 1 over secant squared equals dy dx. Let's keep moving here. Do you know what 1 over secant is? What's 1 over secant? It's cosine? It is cosine. So 1 over secant squared is cosine squared. So this is actually dy dx is cosine squared of y. Now, let's go to the picture and fill this in algebraically. What is the cosine of y? The cosine of y. The cosine of y. Adjacent over hypotenuse. And then it needs to be... Wait a minute, I screwed that up. Adjacent over... Oh, that's a plus sign. Adjacent over hypotenuse. And then it needs to be... Squared. Which gives me... that. It's a beautiful circle. Kind of circle. I don't want to prove all 6 of these to you. I didn't mean to do 2 of them. I just did 2 of them now. It's okay. What we really do is we kind of memorize these rules. So let's say this. I'm going to say it kind of more officially like a rule. Your book says this. The derivative of arcsine of x is this. The derivative of arctangent of x is this. We just proved both of those. Here comes a funny one, arc secant. Arc secant is this one. It's 1 over the absolute value of x times the square root of the x squared minus 1. It's a little different. It's a little different. A little different pattern, but there are these, and it's kind of just these 3 patterns. I mean, haven't I been saying there's 6 of these? Yeah. Well, here's 3 of them. The other 3 are arc cosine, arc cotangent, and arc cosecant, right? Those are the other 3 inverse trig functions. But their derivatives are almost the exact same. Actually, they're the exact same, except they're all negative. So, do I have to write them all down? Maybe I should. I mean, the derivative of arc, I mean, I don't really, you don't have to do this. They're in your book. But the derivative of arc cosine is the same as arc sine, except it's negative. So it's negative 1 over the square root of 1 minus x squared. You guys okay? The derivative of arc cotangent, again, it's negative 1 over 1 plus x squared, right? It's the same as tangent, arctangent, except it's negative. What about this arc cosecant? Yeah, same thing, except it's negative. Negative 1 over the absolute value of x, square root of x squared minus 1. Wow. Yeah. So, this is where I contradict myself a little bit. I'm sorry. So if you're going to memorize these, you don't really, in a way, you don't have to memorize 6. You memorize these 3. And the other 3 are negatives. You know what I mean? In a way, there is 6, but there's not 6. There's 3 patterns, and the other 3 are negatives of those. Of course, then I told you that you don't have to memorize them. So anyway, I'm contradicting myself. I mean, it's cool to be able to have them readily available, but maybe on the test, maybe I'll give you a little sheet of formulas, but not every formula, maybe just these. Hey, what if I wrote these formulas differently, though? We've talked about this a few days back. I've seen your book would maybe talk like this. Watch this, a little differently. The arcsine of u. Now, by the way, what do they mean? Now, see, I wrote my formula with an x. They're writing their formula with a u. We're still doing the derivative with respect to x. They're still going to do the derivative with respect to x, but they wrote a u here. What do they mean by that u? What are they trying to say? Use the function. They're trying to say that u is more than just an x. You guys said it good. You said u is a function of x. I mean, that damn u could be as simple as a 3x, but it could be an x squared, it could be an e to the x, it could be a cosine of x, it could be a, it can be, the u can be its own function of x. And you seem to know that when I asked you, that's good. So how do we write the rule now? We write, say, it's just arcsine. I'm just repeating this rule, but because it's a u, how do I write the rule? 1 over the square root of 1 minus u squared. But because u is a function of x, you got to do the chain rule. And so out on the end, you have u prime. That's me doing the chain rule. That's me doing the derivative of u with respect to x. This is how you write. This is how we write our rules. I tend not to. I tend to write my rules with an x. And then if it's more than an x, I think my class is smart enough to do the chain rule. The book is saying, hey, when we write this rule, don't forget it could be a chain rule going on there. So they got their way of writing it. I got my way of writing it. If it's just an x, that's the answer. But if it's more than an x, if it's a 3x, a 5x, you're spitting out the chain rule. Right, you're doing the derivative of the inside out on the end. Of course you do the chain rule when it's appropriate. Well, that's cool. So now we got all these new rules. Let's just practice them for fun. Of course, it's real fun to see where they show up in a word problem. We are sort of talking about angles now here. Okay, now once we got into this trig and this inverse trig, these things are angles. Anyway, let's just start with this before we do any word problems. Can you handle a derivative like this? So if someone says do this derivative, you don't really prove it, you just do it now, and you've got all these millions of formulas going around in your head or on the board. And anyway, just say something to me. Just a little strategy talk, Product rule, good, that's what I wanted to hear.
Yeah.
You look at that, you got to say product rule, you got to, otherwise I don't know, it's a product rule, there's no doubt about it. And I think I would call that the product. So it's an 8x times an arctangent. Okay, so here we go. The derivative of the first. 8. Cool. Write down the second dude. Write down the second dude. Plus. Write down the 8x. And now I'm doing the derivative of arctangent of 10x. How do you do the derivative of arctangent? Well, it's right here. When it's an x, you put an x in there and you square it. What if it's a 10x? Well, it will, but also you put a 10x in there and square it, right? If it's a u, you put your u in there and square it, right. So it is, the derivative of arctangent is 1 over 1 plus that stuff squared. That's the rule. That's the rule for arctangent. 1 over 1 plus that crap squared. That's what the book says it. 1 over 1 plus that crap squared. Times the chain rule, which is the derivative of that little bit of crap there, which is a 10. And that's it. And this is kind of a mess. Sometimes we like to clean these up. I would say there's not much cleaning to do here because you got this big term first. But this term can get a little cleaned up. 80x in the numerator, do you agree? Over 1 plus 100x squared. That looks a little better. You can clean up that term. But I wouldn't, somebody might think I could factor out an 8. That's true, but not really worth it, if you ask me. Cool. We just did a derivative, and it was a product rule. But I used one of my new rules here. Can you do this one? Oh my goodness. Okay, this is a good one. No here. I would not call this a product rule. I would just do the derivative. There is a constant that's multiplied. See, when it's a constant that's multiplied, I don't call it a product rule because it's a constant. And one of our rules was you could slip past a multiplied constant. So I'm slipping past the 6, and I run into this arcsine, and I'm going to do the derivative of arcsine. The derivative of arcsine is, I got it memorized, it's up there, but it's 1 over square root of 1 minus that crap squared. Is that how y'all talk? Maybe y'all don't talk like that. You're more sophisticated.
Times 5.
Shouldn't call it that crap. Oh, wait, am I done? Right, whoa, am I done?
No, I gotta do times 5 thirds.
I gotta do the chain rule, which says do the derivative of the little 5x over 3.
5 thirds.
That's real simple, although I've seen students do funny things. The derivative of a 5x over 3, you should think of it as a 5/3 x. That's how you should think. What's the derivative of 5/3 x? 5/3. Is that okay with you? All right, I got these up here. They're in my head. They're in the book. I'm going to get rid of them. I'm going to talk about something. Just a second. Listen, I got to come back to this and clean it up. But we did the derivative. Are there any questions about the derivative? You guys are all happy with this derivative? Okay. Okay, good. I'm going to come back and clean it up, but just want to show you one little thing. This pops up sometimes. We're talking about this 5x over 3. Just this 5. If I want to do this derivative, I just did it the smartest way. I thought of it as 5/3 x, and the derivative is 5/3. I've seen students look at this and say, oh, it looks like a quotient rule to me. And the truth is, that's okay. You're working too hard but you could do a quotient rule. It wouldn't be wrong. Let me just help you. If you did a quotient rule, you would do the derivative of the top. 5 times the bottom. 3 minus, write down the top. Now take the derivative of the bottom, which is a 3. What's the derivative of a 3? 0. All over the bottom squared. So these little problems like this do not require a quotient rule. But if you did them, it would work. I mean, if you did a quotient rule, it does work if you do it right. That is a 0, so that whole term goes away. I'm left with
15 over 9.
15 over 9, which is
5/3.
5/3. Oh, that's the derivative. Right. Okay. Anyway, I think I saw somebody doing that on quizzes and stuff. You know, yeah. Same with this. Look at this one. Let's just do another one real quick. Like a 5 over x. I mean, how are you supposed to really do this derivative? Move it up and do a power rule.
Yeah.
Right, that's what you do. You move it up and do a power rule. But, you know what I mean, right? Hang on. You move it up, you call it 5x to the negative 1. So then you do a power rule. What's the derivative? Negative 5. X to the negative 2,
Right.
which is negative 5 over x squared. There's the derivative. Good. That's what you do. You move it up and do a power. Watch. What would happen if you happen to do a quotient rule? You ready? Derivative of the top. 0. Times the bottom, plus, not plus, minus. Write down the top and take the derivative of the bottom. What's the derivative of the bottom?
1.
A 1. All over the bottom squared. Well, that's a 0. So that's gone, and that's a negative 5 over x squared, isn't it? Okay, cool, it works. Unnecessary, though. But I do see people try to do it occasionally, and I just wanted to point out that you really don't have to do it. You shouldn't do it, maybe. But if you do, it works. If you do it right. Yes?
For the second example, that one, if you're taking the derivative, why is 6 staying?
Yeah, there's a difference between, this is just another concept, but like when I do the derivative of 6x squared and I do the derivative of 6 plus x squared, see, watch this. This is important. See, because the derivative of a constant is 0. But that's an added constant or a separate term that's only a constant. His derivative is 0, and so his derivative is 0, and then I do his derivative, which is a 2x. And that's the answer to this problem. And this 6 went to 0. This is a multiplied constant, and the rule for a multiplied constant was you hold it there, and then you go slip past it, and you do the derivative of him, which is a 12x. I mean, maybe I'm over-explaining, but you bring the 2 down, you multiply, you get 12x. You know that. You do a power rule, you get 12x. But what are you doing with a multiplied 6? You're sort of holding it out there and putting it back. Okay, so and that's a common little misconception about constants. But the big theme is an added constant, derivative goes to 0. A multiplied constant just stays there. Right. It's a big difference. And so this 6 was a multiplied constant. It just sat there. I just slipped past it. Okay, good. That's good. Well, you guys, look. So this derivative was done. Are you guys happy with this? Right. All right, guess what? There's a hell of a bunch of algebra to clean it up, kind of. I mean, kind of a lot. Let me help you clean it up. I would, oh boy. Let's see. I think I take my 6 and my 5/3 and put that in the numerator. By the way, if you multiplied it, it would be a 30/3, which would be a 10. So I took my 6 and my 5/3 and multiplied them together. They're both in the numerator, if you ask me, and that turned out to be a 10. Okay, the denominator. The denominator is the square root of 1 minus 25x squared over 9. Is that okay with you? I just squared that. Now, to tell you the truth, though, I'd get a common denominator. And so I would, inside this square root, I would get a common denominator. I would make this 1 be a 9 over 9. Are you guys okay? So now I have 10 over the square root of 9 minus 25x squared all over a 9. Because a 1 is a 9 over 9. You can subtract your numerators over your new common denominator. It's called getting a common denominator. Watch this. I'm going to keep going. Watch this. Now that you got a square root in your denominator, and it has a numerator and a denominator, so what you really have is the square root of the 9 minus the 25x squared all over the square root of this 9. What's the square root of this 9? 3. Holy shit. So now, I think I can do this flip move. I can flip him up. If I flip him up, I multiply by 3 over this square root. You guys okay? Yeah. So now I end up with 30 over square root of 9 minus 5x squared. 25x squared. That's my simplified derivative. These guys simplified big time, as you can tell. Any questions in there? I mean, it's a bunch of algebra steps. I wrote them all out pretty well. Get a common denominator, clean this up. I mean, they clean up quite a bit. Here, you can try one. Try this one. 8 arctangent of x squared over 2. Yeah, try that one, and I'll be right back.